he likes photography, and every year on Queen's Day in the Netherlands, he gets his Polaroid out and photographs people with analog technology. So he is truly multidisciplinary. Tim, the stage is yours.
Thanks. Hello, everyone. Yeah, we buy 2 boxes of Polaroids, give my friends some cameras. I sit on the bench, let them take the pictures, and that way I earn some extra money. Because I'm from the Delft University of Technology, my name is Tim Zaman, and we're going to talk about Rembrandt in 3D, from capture all the way to 3D print, so the entire process. So let's first ask ourselves, what is a painting? Might be an obvious question, but let's look into it. So I have here a painting by Rembrandt. It's a self-portrait from the Mauritshuis, 1696, if I'm not mistaken. So this is a painting. Next to it is a photo of the painting while we're scanning it. And then next to it is a photo of a statue. Now I clearly indicate here that this is a photo of a statue, because you might realize that a statue is 3-dimensional. There was a photographer photographing it, while this is a painting. Just a painting, not necessarily a photo of the painting, because we are usually used to depicting paintings in this way. Paintings are flat. Well, paintings aren't flat. I mean, the world is flat. Obviously it's not. And this is what the artist knew and what the artist used. So if you look at the painting, and I have a 3D print of the Rembrandt right here. And if you look at the turban of Rembrandt, then we can see that in this part, so there, he made indentations with the back of his pencil just to make this illusion of this turban. And especially the late Rembrandt used these methods really to make a sculpture of the painting. And of course there are other facets like time, so the painting really shows its age through craquelure, so that's also clearly a 3-dimensional process. You can pass this around if you want. So this is not the real Rembrandt, this is the 3D print. Yeah, I might as well have thrown it like it was a wedding and whoever catched it could have it, but let's not do that. Anyway, next example. So I have here Flowers in a Blue Vase by Van Gogh. Next to it a photo of the painting. And next to it I put a photo of a cylinder seal. Now I find this very interesting because this cylinder seal by itself is just one structure. It has no color by itself. But you can see what it depicts just because the light shines on it and it gives highlights, it gives shadows. So this clearly is a 3-dimensional object that we can display without it having any color, while the depth deviation is really very small. Same thing counts for paintings, and this is also especially true not only in Rembrandt, but also in Van Gogh. If we look at how he painted, he often depicted these flower petals and made them by just one brushstroke, or maybe 2. And then the light and physics would do the rest. He would cast a highlight, cast a shadow, and therefore it looked like a very nice bouquet, while actually there were just very few paint stripes that he made. Anyway, so our research objective was the design of a topographical imaging device for the near-planar surfaces of paintings, so specifically for that. And the purpose was of moving towards a non-distinguishable, for the normal observer, reproduction. And we want this because we can only achieve this if the material aspect of the painting is thoroughly understood. So if we can answer the question, what exactly makes this painting the way it does? So if we make this 3D print and hold them side by side, if they look visually identical, then we know exactly how the painter painted it, how he made it. So in answering that question, we learn a lot about the painting itself. So the main challenges here is, as I said, a very small depth deviation. So if I put a coin on a painting that I made, not a real one, then you can see that this coin, in reality, it's not really very thick, but the paint itself is even a magnitude thinner. Also, because we want this to be a good reproduction, we need a very high resolution. There's a large dynamic range of color intensity, so you have very bright whites and you have very deep blacks. And we have often a very glossy layer of varnish that induces all kinds of specular reflections, as you can see on the right. And then in the image of the left, we reduce these specular reflections by using a cross-polarization setup just to get rid of those. And we want to simultaneously capture color. So if there's a crack in the painting, we don't only want to see the indentation in the crack, but also the color of the crack, but these need to be registered on exactly the same point. Otherwise, you'll be experiencing some kind of double vision. So these need to be registered at the same time, we thought. So, select the depth perception methods. So we looked at 2 first, so stereo vision, the way our own eyes work. So this is a passive method, only needs a little light to shine. Then we used fringe projection, which is an active method, and then we combined the two to make a fringe projection and stereo vision setup. So So for those of you that don't know, of course, stereo vision is similar to that of the human eye. It needs accurate camera calibration in order to absolutely triangulate one point. But it's very dependent on salient points. So for instance, if I have this minus sign here, both eyes can see it. So both eyes know this point that corresponds to each other, and therefore you can triangulate it. But in this whole white area here, there are no salient points for you to triangulate. You're not really sure and can't really compute by yourself if that's flat. You probably think it's flat, but that's only because your brain interpolates everything that's around it, and you know that this is a flat structure. But otherwise, if you want to know this scientifically, you need some kind of an active method in order also to distinguish these points. So that's where we used fringe projection. And fringe projection I always see as an evolution of the following. So first we have a laser point. So in black I have a laser point there, and let's see this red border as the squared CCD, like a two-dimensional CCD or a sensor that sees something. So if you shine a point from the side and look at it with an angle, you can triangulate, because you know where the laser is, where exactly that point is. Now if you're smart and you have this two-dimensional sensor, you make a line out of it. So you project a laser line, and then you can already see that there's some kind of a structure going on there. And then you can calculate this and triangulate the entire line. If you're even smarter and you think you want to speed things up, you can use multiple lines, as I did here. So projecting multiple laser lines and triangulating all of those. But if you're even smarter and you know that cameras have a tonal range, right? They capture color and gradients. Then what you do is you can use fringe projection. And that looks something like this. So you can already see that there's a structure there. And this uses the entire effective surface of the camera. Now I simplify a lot of these things, but what essentially you do here, you label all the points in your image without the need of this saliency, and both cameras look at them and solve this correspondence problem regardless of the point they look at. So whatever both cameras see, they can triangulate all of it. And this is not dependent on the resolution of the projector. Actually, we blur the projection a little, and then we can use the full effective resolution of the cameras, and therefore we use very high resolution cameras to capture this. So then we combine them together, and what that gives us is none of the disadvantages and all of the advantages. So each point that both cameras look at are uniquely labeled. Then we do the triangulation, so we find the pixel pairs for each same label. Then we triangulate all the points, and this yields one absolute point. So we do that for all the points that both cameras are looking at, and then you get a very large point cloud. This gives us very high data completeness and validity, and we can simultaneously capture the color. This is also what these fringe algorithms allow us to very easily capture the color as well, exactly on the same point where you capture the depth information. And we just get a very high data yield. And this is what we need because we want to capture a big painting in a very high resolution, so we're ending up with a lot of data. So I made a prototype. So what I did is I took two cameras, Nikon D800, so 36 megapixel. We fitted them with Schrammflug or tilt-shift lenses because our object plane was at an angle with the cameras themselves, and so we shifted the plane of focus. So from the top it looks like this, a random projector, two cameras on the side with the Schrammflug lenses, object plane. So we fitted them all out with cross-polarization filters, and we made a printed circuit board and a linear translation axis, as you can see here. So this is a frontal view. And this is another view where we were actually scanning the Rembrandt. No idea where it is at the moment, but I hope they'll be okay. Anyway, so what we did is we connected all of it together. What we needed to do then was the software. So we did the hardware I/O. We needed to come up with a smart calibration routine, because that was very important to get this high data validity. We did color management, also very important, maybe one of the most important. You need to have the color correctly if you want to go to 3D, in this case, for paintings. We made a graphical interface to make things easy, so I made the graphical interface, and then these days someone else can scan and they don't need me anymore, so that's for me a lot of fun, because scanning paintings is nice, but when you've done it 10 times, then the fun's off, I can tell you. Yeah. They often thank me, wow, Tim, it's really an honor for you to sit here with the paintings. And I'm like, okay, yeah, I've been here too many times already. Anyway, so, and then we need to implement, of course, the fringe and stereo algorithmics as well. And, of course, the data stitching is what we solved as well. So the performance eventually, it takes around 10 seconds per capture. It takes around six captures. The processing time is only 1 minute because it's if you've written it out and you make it into a good program, then this labeling and this triangulation procedure is really very trivial. This leaves us with usually 30 million points inside of the point cloud because the camera's at 36 million pixels. And the effective resolution, so not the sampled resolution, is then 50 by 50 by 10 microns. So it's very small. So it's around 500 dpi's if you look at it in printing terms. The cost was only $600. Because I'm from the Delft University of Technology and I hadn't had a budget yet, so my professor said, well, you can use a little money and you can make this. So the cameras I borrowed and the lenses as well. And the timeline of the entire project from making the scanner, working together with OSE, making the 3D printer, and scanning it and making the eventual print took around 8 months. So practical test, we did 3 at first. So that's a self-portrait, as there's somewhere in the room here. The Flowers in the Blue Vase by Van Gogh, and the Jewish Bride by Rembrandt. The Jewish Bride was quite big, 1.60 meters by 1.20 meters. So that was a billion pixel point cloud. So let's look at the self-portrait by Rembrandt. So this is how we scanned it. So we have the camera in front of the painting, and then we just set up a simple desk, and then we did the processing. I think this only took a few hours or an afternoon to scan this work. Then if we look at the data, so this is the part in the turbine where you use the back of a pencil to cut something out. This is 5 centimeters, so this big. This is 3.5 centimeters, this big. And now we're going to look at the depth data. So we're looking at the depth map now. And if it's black, it's far away. If it's white, it's close to us. So you can clearly see the scratches that he made with the back of his pencil. And you can see actually that when he made this scratch, he not only made an indentation, but also he moved the paint away. So this gives a structure to the front. You can see all kinds of microstructures. These are larger pigment particles because they used to ground their pigment by hand. In the top right, you can see part of the canvas, like the bulges of the canvas that's underneath. That's also in the reproduction that's going along here. And if we look at the other part, where the cracula was, so there's cracula here, same thing counts. Let's take a cross-section and look at this cross-section in the graph. And this cross-section, again, this is 4 centimeters wide, and this is 0.3 millimeters. So that gives a good idea of how thick this is, not very thick. And we can see, actually, the indentations of the cracula up there. So if you look at this crack, there was something that worried me. So I said, well, probably our data is not correct, because there is a crack indeed, but the sides of the crack are coming up. So I sent an email to the conservator, and she says this is a clear case of delamination. Because what happens is there's a crack here, but the paint actually cracks apart and then splits open a bit. So that's actually what we're seeing here. And this is so the first stage of delamination. And if you let this go without helping the painting by itself, the paint flakes might eventually fall off. So this kind of data can also really very well be used for conservation purposes. So if I now take this scale, the X scale and Y scale, and put them 1 to 1, you can actually see that the painting effect is as flat as a pancake. It's really very flat. So let's look at, so this is one capture, and we're going to fly over it now. This is the bottom left of the Jewish Bride. You can see, this is the side of the painting. You can see 3 global cracks running along, and a lot of interconnected smaller cracks running along the sides. And then I have this other image. This is part of his sleeve, actually. So Rembrandt painted the sleeve. And later Rembrandt, he was so good at this that he didn't meticulously paint the sleeves, but he just took some paint and put it on there, and he knew that it will eventually look good in the illusion of this sweater that he was making. And indeed he did. And they still don't know exactly what he did to make this paint so thick and how he put it on there. They think that he mixed it with honey and just put it there with his palette knife and let it dry. So he really worked with paint as if it was a sculptor. Yeah, I think that's this one. So you can see really the very big valley. So this is quite thick paint. This is almost like 5 millimeters. And they say he put it on with his thumb, and then he cut one part, just cut it off. So eventually we also, of course, did the printing of this. We worked together with OSE to do that. So what we did is we had these three paintings. We captured it, processed it, printed it, and then out came the other paintings. So first we captured it, and it looks like this. So it just goes, as the ox plows, we go along the painting, capture, 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 capture. Then we did the processing. It was very boring to look at, but I seriously got an alert warning. Your CPU is at 95 degrees. So I was okay, it's centigrade, so that's very warm. I was like, okay, that worked out fine in the end. And then the printing, that was done by OC. So the process was, maybe I need to click again. Yeah, so the process was inkjet. So you can see here the sides of the print. This is that sleeve that I was talking about as well. All reproduced, all the tiny cracks, all the parts of the canvas. And here you can see the paint moving. So depositing layer upon layer upon layer of ink, just ink drops. Then they cure, you build it up, and then what you get eventually is the entire painting. So this painting was this big. I couldn't take it with customs with me, so I thought, no, that's all right. So I took this one. It's quite smaller. So there we have it. We made new paintings from an old painting. So it's like a derivative. So that brings us to the question, what does the conservator think about this? But first, let's look at the ultimate reproduction. So the concept of authenticity really requires an original to exist in the first place. So this was the Van Goghs that we looked at with the conservators. And you can see that the color reproduction is quite accurate. They're almost both the same, only ours wasn't printed on canvas, but it was printed on whiteboard. So that kind of gives it away. But really visually, from that distance they were looking at now, that looked very similar. So the question is, what is the value still of an original if we can make an ultimate reproduction? So in the end, there might not be a theoretical difference. So they thought about this 100 years ago already, when they saw the photography coming up, and Walter Benjamin in 1936 already said that only the aura will remain. So you're standing in front of this painting and you think Rembrandt stood here as well and really painted this and decided this, and it was another time, so you can really imagine it. While this painting that I'm giving around now, it's like, yeah, I have this painting, Tim just passed it around, it probably has no value. So you don't get that gut feeling like, wow, right? So that's really the difference. But let's look at authentic art. So, well, this is authentic art. This is, of course, the Mona Lisa by Leonardo da Vinci. Well, that's by everyone considered to be art, right? So next to it, I have a derivative of this work, which is also considered art. So this is the same Mona Lisa by Marcel Duchamp. I think he took a postcard, maybe from the museum. What he did is he painted on a moustache, as you might see, like a nice one, and named it LHOOQ. So if you pronounce that in French, which he was, it's LHOOQ. And that's French for there is a fire down below, so to speak. So this indicates, and this is also considered to be art. It's like a form of modern art, but still it's art. And it's very derivative, of course. And the nice thing is that he took it one step further, or maybe even one step back, and he did it again. He made a Sibyllin one. He removed the moustache and said the same thing, LHOOQ, Razi, so shaved. She's been shaved. So what we end up with is, again, the same work, which is extremely derivative, of course, but it's still considered to be art. If we even take it one step further, then some arts are by itself derivations, right? There isn't an original, that's the project, it's the derivative, that's the piece of art. So this gives us already the feeling that a 3D print by itself, as in the way that we did here, could be considered as art as well, by itself. So then we looked at the adoption of the 3D reproductions by the expert. So Ernst van de Wetering, he's the world's leading Rembrandt expert. He's the head for 30 years now of the Rembrandt research project, and he really loved it. He really loved to touch it for the first time, and he was like, wow, and he was like waving it around and looking at how the light worked with it. So that was really the first time that he could actually do that while he was busy with Rembrandt, I think for all his life already. So he wasn't like, oh, what's this? This is like, what do you come to me with this? And he was really very open to it. He didn't say that he would hang it in a museum, but he saw it as a different kind, like as you would have a poster on the wall. I mean, you can still appreciate the art in this way. Maybe it doesn't have the same aura, but it's still a good way of appreciating the actual art itself. But you could also imagine that you would hang this in a museum. If you have your work on loan, you can just hang this up there. Or if you're very careful with your pieces, you have these in the depot and hang on there these prints. If you're a smart museum, you open a museum shop and just sell them there. Because I think there are a lot of people that really like Rembrandt know they can pay for it, but they want an accurate reproduction, and I think this is the next level. So our future work is improving the reproduction by adding varnish and translucency, because what conservators see here, so if they look at them one by one, and we thought we were making the identical reproduction, right, the ultimate reproduction, by doing this in 3D, well, that's not the case. There are other things that we didn't foresee that are very interesting, very important in experiencing these paintings. For instance, translucency and optical effects. They used lacquers and they used varnish, of course. And all these things, they come to play with experiencing an art piece which looks real. So we're now still in the process of looking underneath the painting, looking at these layers, looking at how the light works in these optical effects. Moreover, we're also into making full body scans. So most paintings that we do, we take XRF images of, we try to OCT it, we try to do the 3D scanning. We make a normal photography, hyperspectral imaging, and we try to all combine these different images in order to have a full body scan of this painting, so that we have all the pieces of the puzzle in order to, let's say, recreate the painting or recreate what the artist intended. For instance, there are some components in the image that might discolor, right? So cobalt blue, for example. Cobalt blue really degenerated it. So it was blue in the past, but then it got brown again. So that means that how we perceive a painting today might not be how the artist actually intended it to. So what we could actually, in theory, do with paintings like this is actually make a painting that looks more like the original, as the artist intended it to, than the painting today. Right? So that's something to take home with you. So I'd like to acknowledge the Rijksmuseum, the Mauritshuis and Krüller-Müller Musea to work on us with the first 3 pilots, and OC for doing the 3D printing and making the printer. And that was all for my talk. Thank you very much for listening.